Hello everyone, good morning. Today we are going to be, again, changing a bit of cosmological observables because we are going to be describing some of the measurements involved in the other main cosmic tension that we have uh, between our experiments today. And this one is related with clustering between the predictions that we can get from the observations at high redshift and the observations that we have at low redshift. So historically, at low redshift, the amplitude of the matter perturbations has been quantified in terms of sigma 8 square, which basically is the variance of the perturbations, of the matter perturbations on a scale smooth over 8 megaparsecs over h. So this would be directly the integral of the matter power spectrum, usually at redshift 0, if nothing else explained. This would be the whole variance, and we want the variance when our map has been smooth on this scale. So here we have some window function that is the Fourier transform of a top hat in configuration space with radius of 8 megaparsecs over h. This is basically a historical convention which is very problematic because from the early universe and from our description of the cosmological model, we are expressing all the time the amplitude of the perturbations in terms of AS, which is the amplitude, if you remember, of the primordial curvature power spectrum. So for lambda CDM, of course, this is easy. The transition between this and this depends directly on the transfer function, which basically is going to depend on these scales on the matter abundance. So it's going to be okay. But the problem is when we go beyond lambda CDM. As we will see between today and tomorrow, there are some discrepancies because when you start adding components or considering new pieces of physics, the constraints and the clustering at lower redshift and smaller scales may differ from their assumptions for lambda CDM, and therefore the connection between these two is not one-to-one. And in this, we will get into more detail tomorrow, but there are some confusion and some freedom just because of how we phrase the amplitude of the power spectrum at redshift. But yeah, basically what we can get from the comparison between the CMB and the evolution within lambda CDM and the constraints that we get for the amplitude of the power spectrum today is that at the smaller scales and lower redshift, we observe the universe being more smooth. The perturbations in the matter are smaller than what is predicted from the lambda Coldar matter. So today, I'm going to be talking about probes of clustering. So the main probes that we can find and we can think of for the matter clustering are basically different probes with tracers of the large scale structure, and here we will be measuring directly its clustering or its abundance. And this one, for example, would be the galaxy power spectrum, or if you go to smaller scales and higher redshift, you can measure also the power spectrum of the Lyman alpha forest. But the problem with this, as I think I mentioned maybe quickly on Tuesday, is that yesterday it was. You have the problems with the redshift space distortions. You observe the position of the galaxies not measuring directly at distance, but it's redshift, so it's affected by the peculiar velocities, which at low redshift is very hard to predict. Sorry, at low redshift, not at smaller scales, when you start considering non-linearities. And also, you have the problems of the bias, the relationship between the distribution of the tracer that you are looking for, and the matter distribution that is what you're interested in. So here, the problems are RSD, receive distortions, and bias, of course, both of them in the nonlinear regime, and therefore, when you go to smaller and smaller scales, especially for the galaxy clustering, the uncertainties in the theoretical modeling are such that you usually can't get to very small scales. Current smallest scales, probes, for example, with galaxies are k around 0.3 inverse megaparsecs over h. Also, due to probably this limitation, even if the pros of clustering with the galaxy, especially with galaxy clustering, is very powerful to constrain some feature of cosmology, especially with the lambda, with the BAO, but also with some of the shapes of the broadband, if you use some approaches like the effective field theory to describe the whole power spectrum, the biggest tension in terms of sigma 8 is not with probes of the large-scale structure clustering, but with gravitational lensing. Gravitational lensing is basically the effect that the gravitational potential have in the propagation of light by bending its path. Yesterday, at the end of the class, we talked about the effects of and the situation in the strong lensing regime. Today, we're going to be covering especially the weak lensing regime because it's the one that is more sensitive to the perturbations in the large scattering. Too many LSS in the large scale structure. So this would be weak lensing, and there are different ways that you can probe the gravitational potential with weak lensing, and we are going to be covering those. The main are CMB lensing, which would be the effect of the gravitational potential in the propagation of the photons from the CMB, and the other would be the effect that the gravitational lensing has in the actual shapes of the galaxies. Now, the measurements of gravitational lensing are much more complicated than the measurements of clustering because you don't have, the measurements of clustering are kind of easy. You measure the position of galaxies and you just take its power spectrum for how they are distributed. In the case of the gravitational lensing, you need to take into account the measurements of the shape of the galaxy and how they may have been distorted. However, it's in the theory, it may be cleaner because you don't have problems with redshift space distortions or the bias of the tracer. So, give it or take has some pros and cons. And the fact that it does not rely on the bias or on redshift space distortions also allows us to probe much smaller scales in the matter power spectrum. Okay. So we will be covering, as I said, just mostly gravitational lensing, and we are going to start with the basic of lensing. So basically, the effect that the gravitational potential has in the photons, on top of the redshift that they may create, but in terms of lensing, is just, it's the deviation of its paths because it creates new geodesics. But if we are focusing at redshifts after recombination, there is no free electrons, so there is no collision term in the Boltzmann equation. And for the photons, the phase space distribution must be constant. So, and this basically means that the only effect that lensing has in the photon itself is going to be only in its polarization and also in its intensity, but not on the actual state of the photons, but how we observe it. So let's focus first on what a telescope observes. A telescope, what measures is the integral of the specific intensity that, if we compare it with the energy of the photons, can be described as the energy per solid angle in the sky that goes through a given surface, now at Earth, in a given period, moment of time, and in a given frequency bin. So if we think that for a given fixed interval time, we are going to be measuring photons in a volume that comes as the surface that we have in order to be detecting the photons time that time interval. And also, since in natural units, the energy of the photon goes as the momentum, which is 2 pi times the frequency of the photon, we also know that the volume element in momentum space is equivalent to 2 pi cube, nu square d nu, and then the solid angle that we receive photons from. So from here, basically we can translate the expression for the specific intensity in terms of the phase space distribution, because we know also that the energy that we observe is the number of photons that we receive times its energy, and the number of photons that we have, it's 2 times the distribution function, where these two basically is the energy of the photons with its spin, the volume element in phase space over the normalization of the volume element that goes as 2 pi cube. So now, if we put all this together, what we have is that the specific intensity of the photon goes as 4 pi nu cube, the phase space distribution. And here we have already a couple of very important results. Since we know first that the phase space distribution from the Boltzmann equation is not going to change, we already see here that the specific intensity over the frequency to the cube is a constant. And also, we need to compare some specific intensity that we know that is not going to change for a given frequency with the fact that we have discussed before that what gravitational lensing does is change the position on the sky that you are going to observe the source. So basically, the specific intensity that we observe from some given angle on the sky is equal to the true specific intensity, which would be the unledged case if there was no perturbation on the path of the photon, in the unperturbed position of the source, where basically the geometric system that we have here is we have some deflector we observe from here, and we have our source here. So if we observe from here, this would be theta s for this location. But when we observe this photon that has been perturbed, we are actually observing it here, right? So this would be the position that we have, and this is the image. Now, of course, this geometric cartoon is very exaggerated because we are going to be working on the weak lensing regime. So we are expecting the deflection angle between theta s and theta being very small in such a way that we can work on a flat sky approximation. So we are going to work on flat sky approximation, which basically means that we are going to work either with 2D angles from the 2D vectors from the angle, which is just on this plane, or in Fourier transform. In Fourier space, we are going to work with vectors for the vector L, which would be the Fourier counterpart of the angle in the flat plane. And since we have in weak lensing regimes, if we say that theta s is theta plus some deflection angle, this is going to be very, very small, and we can work on linear order. Okay, so now let's try to break down the coordinates of this system. Since we are on that flight approximation, we are considering that the distance of both the image and the source to us is the same. And the three-dimensional position, and here we have either the image or the source, is if we work in perpendicular and parallel to us, this would be the distance, the moving distance for both of them, given either theta or theta s, and 1. So basically, the name of the game that we are going to do is describe theta s as function of theta, which is going to depend on this deflection angle that I mentioned before. Okay. In the case of, in order to see how we can describe theta s, we can write it just from there as the position perpendicular to the line of sight over the distance. And if we are able to describe this as a differential equation, as a differential with respect to the distance towards us, we can just do the integral along the line of sight and see everything that has gone in how we observe what would be the position there. So we can just transform this into an integral in which we are going to have from 0 to chi delta chi and prime, and we have the differential dependence between the position and the distance to us. And one trick that we can do here is that the chi is equal to minus the conformal time. And this is because the distance we are measuring from us towards the farther away, so earlier in time, thus we have a minus here. And this is minus dt over a, in such a way that this is 1 over the distance, the integral from 0 to some distance, delta chi prime, and we have minus dx as function of time multiplied by the scale factor. And this is, by definition, the physical momentum. So at the end of the day, we have the integral of the direction of the physical momentum around the direction perpendicular to us. The good thing is that we can get this as a function of the time and do the same thing, how this has been built well on the line of sight, if we write it in terms of the geodesic. So from the geodesic, we know that minus I dp over the time, it's just the gradient, again, perpendicular to the line of sight all the time, of the difference between the two potentials. And assuming that we don't have any shear, we have minus 2 delta perpendicular to us over the gradient of the gravitational potential. So now basically what we can do is we plug how the momentum perpendicular to us builds as we integrate over the line of sight, and it depends on the gradient of the gravitational potential. So at the end of the day, we have the position as function of two integrals with respect to the line of sight. Now, if we change a bit the order, we have that theta s is equal to where we observe the image. If there's no gravitational potential, we observe the image exactly where the source is, plus some deflection angle, which is 2 times the integral along the line of sight between us and the distance that the source is, of the differential of the distance over the distance, the gravitational, the gradient in angle coordinates on the plane of the gravitational potential along the line of sight, which is given by the position at the given angle and the given distance, and how it evolves with respect to time, times 1 minus the distance that we are integrating over divided by the distance of the source. Where here I have defined, just by the change of variables, that the gradient in physical distances perpendicular to the line of sight is equal to 1 over the distance, the gradient in angular units. So basically what we have is that we can write the deflection angle as some gradient, angular gradient of our gravitational potential along the line of sight. And since this does not depend on the distance, we can get the gradient outside and express everything as some gradient of a gravitational potential. And this is going to be, this lensing potential is going to be the main quantity that we're going to be dealing with for gravitational lensing, and is this integral along the line of sight of the gravitational potential weighted by this kernel that involves some distances for the geometry of the lens equation. For example, one of the features of this kernel is that as we get close to the source, that means that tilde chi is very close to chi, there is not effect of lensing, as we can imagine from the system that we were having. And basically, by projecting all the gravitational potential along the line of sight, what we are doing is that we are not caring only for one single lens, as in that drawing, but by all the perturbations that we are going to find along the line of sight, because some of them are going to be over densities, so they curve the light in one direction, but some other are going to be under densities, so we need to take into account all that. Okay, so we have that the deflection angle it's the gradient of the lensing potential, but this is good and this is useful when we are looking to diffuse images. When we are looking to point sources, we are going to be that source changed in the sky, but we are not going to know what was the initial position of that source. So we are not going to be able to get information from that deflection angle, and what we are going to need is the distortion angle, how that source has been distorted, because as you can imagine, if we change theta here, the gradient is going to be different, phi is going to be different, and the deflection angle is going to be different. So we are going to also need the anisotropic dependent of this deflection angle in such a way that we can define the distortion tensor as the second derivative in different directions, well, on the two directions of the gravitational potential, which is what is going to be used for cosmic shear. Okay. Clear everything so far? Okay, so then now we are going to discuss about the two main observations that we can use lensing with, that as I anticipated before, are basically the CMB lensing and the cosmic shear of the weak gravitational lensing on galaxies. Okay. So on Tuesday, we described the CMB anisotropies and the CMB power spectrum, but one of the main assumptions that we made is that the photons, after the large scattering surface, they would evolve freely and free stream until it reaches us and we observe those anisotropies, but that's not exactly true because the universe is not empty as they travel to us and it's not homogeneous. So as they encounter the gravitational potential, they are going to be lensed. As they encounter free electrons, they're going to scatter, and so on and so forth, in such a way that there are also secondary anisotropies to the CMB. And these secondary anisotropies are called secondary, in contrast with the primary anisotropies that are the ones that depend exactly on the properties of the photon at the large scattering surface. While the secondary anisotropies, like lensing, depends on changes and perturbations that these anisotropies suffer as they travel from the large scattering surface to us. So in this case is how lensing applies. Weak lensing applying to any diffuse field in which we don't have a specific detection, we just have a map of intensities. Now, in cosmology, the only one that so far can be exploited with this kind of diffuse field is the CMB, but this would also apply, for example, two observations of line intensity mapping to 21 centimeters. The problem is that these observations are much fainter, the noise is larger, and the effect of weak lensing is going to be super small and probably won't be able to be observed at any point. Okay, so working on the flat sky limit, we have that the observed perturbation that we have that comes from a given position on the sky corresponds to the true primary anisotropy at a given angle plus the deflection angle. So we need to take into account this deflection angle when we move from the observed to the true one. And this is basically the only effect that affects the diffuse fields because, as we saw, the specific intensity at a given angle is the same as the unperturbed one at the angle that the original source is. So what we can do right now is just expand this. And what we're going to have is the original anisotropy at the angle that we are observing plus the deflection angle in a given direction times how, how the anisotropy changes with respect to the angle, plus the second order term in the expansion that relates with the distortion tensor. Because it depends on the two derivatives in the two directions for the observed or the intrinsic temperature perturbation. Since it only affects the angle that we are observing the temperature perturbation from, weak lensing also does not affect the mean temperature of the CMB. So we only detect it at the power spectrum level. Sorry. So in order to measure and see how this affects to the power spectrum, we can just take the power spectrum of this quantity in Fourier space. Since we have a two-dimensional space here, because we just care about the plane that we have, we just need to change the, so substitute the deflection angle for what we have here. And each of the derivatives is going to be a factor I times L, which is our Fourier wave mode here. So in this case, we have that the observed temperature as a function of L it's the original one and it's just the Fourier transform of all these over 2 pi squared L prime L minus L prime, the lensing potential evaluated at L minus L prime, the original anisotropy at L prime, minus 1 over 2, and here we have two integrals. And we have all the terms here. L prime. where anything that appears just after the anisotropy or the lensing potential is where these are evaluated. So this is L prime times L minus L prime times the lensing potential evaluated at L minus L prime times the anisotropy evaluated at L prime, and so on and so forth. So from this, basically, we can just compute the power spectrum by taking the variance of this to the first order in the lensing potential, where in the lensing potential power spectrum, which is the variance of these two quantities, and we can define it as phi L of L, phi L of L prime, as we have defined any of our power spectrum. Okay. So we can take the variance of this, which is going to be this times its complex conjugate for another L, and use this same definition of the power spectrum in general to see how is the power spectrum of the observed temperature anisotropies. And now, for example, for those of you that are not very familiar with how we compute power spectrum, I just wanted to say that this is the flat sky limit of what we saw on Tuesday for the expression of the power spectrum that depended for the CMB, that depending on the Kronecker delta for L and M. That will be the full sky approximation. So accounting for all this, we have that the observed power spectrum of the temperature perturbations is going to be the intrinsic one plus some integral of L prime times L minus L prime squared times the lensing potential power spectrum evaluated at L minus L prime times the intrinsic temperature power spectrum of the CMB minus the primary CMB power spectrum, and here is just an amplitude of L times L prime squared and the integral of the lensing power spectrum. So this is to first order in the lensing power spectrum how we observe the power spectrum of the CMB. And we see the main two contributions here to how lensing affects the temperature power spectrum. On one hand, we have some damping term here, that, like this is the last term, that is basically an additional damping on the CMB power spectrum on the scales corresponding to the deflection angle, and this is basically because as the photon travel, they're going to randomly encounter over densities or under densities in such a way that the deflection angle at very small scales is going to be random, and that's why you lose coherence in your perturbations and the power spectrum gets damped. But we have another term here, this addition, that is basically a convolution between the anisotropic power spectrum and the lensing power spectrum. And that basically what it does is that on the one hand, it smooths the peaks of the CMB. So if we had something like this before. Now we will have smoother peaks here. But also what it does is that this power that is subtracting from larger scales through the convolution is transferred to smaller scales. So at the end of the day, there's going to be some contribution here at very small scales on the lensing power spectrum due to this transfer from large to small scales of power. Okay, so we're almost done with the effects of the CMB, of weak lensing. This is how it affects the temperature power spectrum, but as you can imagine, since we are perturbing the direction of the propagation of the photons, there's also going to be some effect in the polarization of the CMB photons. We haven't talked at all about polarization, but just as a curiosity, or because maybe you have heard, this is why lensing introduces a leakage between the E modes of the linear polarization of the CMB to the B modes that, in the absence of secondary anisotropies from primordial perturbations, if we don't consider tensor perturbations, they are not generated. So any B mode that we observed is if we only consider scalar perturbations, is going to be produced from this leakage. And this is why lensing is such an important contaminant in order to the quest to try to detect the primordial B modes in the CMB power spectrum. Okay, so I think that it's a good time to take a short break. After the break, we are going to cover how we can get directly the information about lensing from the CMB. Okay. So, yeah, just before going and continuing with what information we can get about lensing from the CMB and the effects that the gravitational potential have in the propagation of the photons, just a couple of things. Just to be sure, because there were a couple of questions about it, the gravitational potential, it's basically this integral which corresponds to the projection along the line of sight of the lensing potential is this integral, which is the projection along the line of sight of the gravitational potentials weighted by the geometric relations of the lens equation. So basically, this is a way to, since lensing is an integrated effect, it depends on everything that you have along the line of sight between the source and you. It's a way to quantify in a very specific field all of these effects, and everything is going to depend on how this lensing potential depends as we change the position of the sky. That's why the diffraction angle is the gradient of the lensing potential, and the distortion tensor is the second derivative of it. Then what we compute right now for its effects on the CMB is basically how this lensing potential introduces small corrections on the observed and measured CMB power spectrum with respect to the predicted one that would be only accounting for the primary anisotropies, if there was no lensing at all. And we have basically computed this with our definition of the angular power spectrum that we always tend to care only for the power spectrum about the diagonal term of this covariance, in which L is equal to L prime due to this Dirac delta here, and we compute directly that variance. This is what we measure directly from the power spectrum, and the effects were this transfer to small scales of the power and the smoothing that I mentioned. However, as you probably may be already seen from how we observe the anisotropies as function of the primary anisotropy, lensing has a much stronger effect than just modifying a bit the diagonal of the covariance for the CMB anisotropies, and it also generates some off-diagonal terms in this covariance, and this is basically because lensing breaks the perfect isotropy that the CMB has been unperturbed. So basically, we have all these modulations at very small scales for the observed anisotropy, but since these modulations depend on the lensing potential that in turn is basically depending on the gravitational potential, we can expect these modulations to be correlated at very large scales because of the power spectrum. So for example, if we have here some map, and this is, and like lensing is changing this patch in smaller scales of the CMB in a specific way, how lensing is changing this patch at this long distance is going to be correlated through how the large scale structure is correlated in the sky. So we can try to extract that information from the CMB and how the lensing affects the CMB. So, as I was saying, there are some off-diagonal terms. So instead of computing the power spectrum for this specific diagonal part, what we can compute is directly the observed power spectrum, but specifically for the off-diagonal parts. Okay, and if we basically squared these parts for these arguments and take into account that L is different than 0 and so on and so forth, we end up obtaining that we have some capital L minus small l times capital L, the power spectrum at evaluated at the difference between how far we are from the diagonal, plus a small l times capital L of the power spectrum times the lensing potential at capital L. Basically, what this is computing is how the power spectrum in this, the off-diagonal variance in this specific patch depends on the lensing potential around that part. So basically, from the CMB, just looking at computing the power spectrum as usual, the covariance, but looking at the off-diagonal terms, we can reconstruct the lensing potential. So if we have this kind of dependence here and this kind of modulations of the diagonal terms, what we can do, and this is very common on any study of the CMB secondary anisotropies, but you can find it in basically any effect that you can think of small scales modulated by very long modes, we can develop a quadratic estimator in order to try to reconstruct this lensing potential. So in this case, the estimator for the lensing potential as function of the wave mode capital L is defined as some normalization that depends on the mode times the integral of the observed anisotropies but like weighted by a series of weights that depends on small l and capital L. So basically we can convoluting these two terms, sorry, and this is at the end of the day, from the convolution of these two terms, weighted by this set of weights, we can create a reconstructed map of the lensing potential. And this is called quadratic estimator, basically because it depends on these two factors. The only thing that we have left now would be to determine the normalization and the weights. And basically we can do that, as for any quadratic estimators, enforcing that the estimator is unbiased, which means that the mean of the lensing potential is 0, and minimizing the variance. Because when you are computing the variance, at the end of the day, basically you have also here is accounting for the phi dot that also includes foregrounds, includes noise, and so on and so forth. So you want to minimize that. So by using this quadratic estimator, basically what you have at the end of the day is some reconstructed map as function of your wave mode or your spherical harmonic modes, if you are in the full sky limit. And from there, if you turn it back to configuration space, you end up with a map of the lensing potential, or a quantity that can be maybe more interesting and is more physical. We can think more about it, some convergence map, which is just the half the Laplacian of the lensing potential. Which is basically, if you take it from here, this is some of the elements that appear on the trace. This is half the trace of this factor, or like the distortion tensor. So since this depends on basically the Laplacian of the lensing potential, and the lensing potential depends on the gravitational potential, we can insert this inside and compute the convergence as function of the matter density using the Poisson equation in such a way that kappa is also equal to 3 omega matter, the Hubble constant square, over 2, and then the integral that we have there with some additional factors from the Poisson equation. Delta M of theta chi Okay. So basically, from doing the reconstruction of the lensing potential using the quadratic estimator, we generate a convergence map that depends directly on the projection of the matter perturbations. So if we apply this estimator to the maps, for example, from Planck, we can directly take its power spectrum, and this is what is called the lensing power spectrum from Planck, the CMB lensing power spectrum, that Planck can measure it reliably up to scales of L equal 400, if I remember correctly. But the problem that you get with that is that you get, sure, a lot of information of the matter perturbations, but this information that is very degenerate because at the end of the day depends on a line of sight integral from 0 to the distance to the last scattering surface, which at the end of the day corresponds to a kernel weighting the integral that goes something like this, even flatter. So like this would be the kernel that integrates delta m as function of redshift, peaks kind of like at redshift around 2, but then you get many of these. So in order, if we want to extract some more clear information about this, we need to do something else. And this is basically what is called CMB lensing tomography. We have something that depends on the integrated matter density along the line of sight, but is basically the projection of the large scale structure. So if we cross-correlate this lensing, this convergence map with any other tracer of the large scale structure, we're going to be getting, first of all, cross-correlation, because both quantities, both maps, would be following the same distribution of matter. But at the end of the day, if we cross-correlate all this projection with, for example, a galaxy catalog that is specific to a redshift bin, the correlation is going to isolate the contributions of the large-scale structure in that specific redshift bin. Because imagine that we cross-correlate this with some galaxy catalog that in redshift, I don't know, has like this redshift distribution. Anything that happens for the large-scale structure at higher redshifts is not going to be correlated with this, because they don't know, it's just a different distribution. There's no spatial correlation. So basically, you can think about this kind of cross-correlation in lensing tomography as just taking a slice here and getting the information about how the large-scale structure affects the CMB lensing at this specific range. So by doing this kind of cross-correlation, at the end of the day, we are doing tomography, and this is why it's called lensing tomography, of the CMB lensing and the convergence to up to the distance of the large scattering surface. Okay, any question regarding CMB lensing? Then if not, we are going to spend the last half an hour of the class today going beyond the deflection angle, thinking about the distortion tensor, and considering how we can measure weak lensing from, instead of from the CMB lensing, from the distribution and the distortion of the shape of galaxies at much lower redshift. Okay. So in this case, we are going to care about how lensing distorts the photons that come from galaxies at low redshift. But since we don't know, these are point sources at the end of the day, or they are resolved, but they are located on the sky. So since we don't know which is the original position and the perturbed position of those sources, we cannot use the deflection angle. So we are going to care about galaxy weak lensing. And here, the important quantity, rather than the deflection angle, as I was saying, is the distortion tensor, because if we have some galaxy that we observe with some point spread function at the end of the day from our telescopes, if we have our origin exactly at its center, the lensing potential, sorry, the deflection angle here is going to be different than here, such as, like, for example, if these two are in such a way that they point towards different directions, we are going to end up observing, so after lensing here, the galaxy with ellipticity. And it's this kind of distortion in the shape of the galaxies, the one that are targeted in galaxy weak lensing. Now you can imagine that this is a much more complicated measurement, because first of all, we don't expect all the galaxies to be just a circle that we distort. So we need to observe lots and lots of galaxies sorry, to average out the intrinsic shape of those galaxies. Also, we need to be, since we need those many numbers, we usually can't detect that many with spectroscopic surveys, that are the ones that give you very good redshift determination. So we are going to use photometric surveys, and since we need many of these galaxies, we are going to be pushing a lot on the luminosity function of these galaxies, so most of the galaxies are going to be very, very faint, which makes the measurement of the shape even more complicated. And just by itself, this effect of creating the shear is very small by itself. So we need to resolve all this. But since we are basically going to describe some change in the shape, we need first to be able to describe somehow mathematically the shape of a galaxy. So in order to do that, basically the way to do it is defining the zero position in the center of the galaxy. We can describe the the shape by taking moments in the radiation that we get from it as function of the position. So for example, the zeroth moment is directly the flux, right? Because it's just the angular integral of the whole observed intensity that we receive from the, that we receive from the galaxy. The first moment, since it will be basically a whole deflection, but we are centering always the position in the at zero, is equal to zero with this choice of coordinates, and we don't care about the deflection angle, the overall deflection angle, so it's okay for us. And the second moment is what we're going to call Qij, which is just the weighted angular integral and in order to make things easier, we can work with this matrix directly as if we defined as 1/2 of Q, 1 plus epsilon 1, epsilon 2, epsilon 2, and 1 minus epsilon 2. So here we have Q, that is the trace of this shape, and basically gives sense of how big is the shape. If Q is larger, this is a larger circle. If Q is smaller, it's smaller. Sorry, I forgot. This is normalized by the flux. So basically, Q gives the whole circular size of the galaxy. And epsilon 1 and 2, which are the traceless components of the tensor, basically gives you the two ellipticities in the two directions. So if some of you remember about light polarization, this is a tensor that is very similar to the tensor describing the linear polarization with the Navier-Stokes parameters, in which Q would be equivalent to I, and Q and U, so small q and Q and U from the linear polarization, is equivalent to the ellipticities here of the shape. So we can use all of the algebra and all of the intuition that had been developed before for the CMB polarization, or just in general, the intensity and polarization of light. So just as a spoiler of what we're going to end up doing in the end of the day, we are trying to describe this shape and how it's going to be distorted by the distortion tensor due to the lensing potential in terms of E modes and B modes. Okay. So we have already a description of the shape of the galaxy. This is the intrinsic shape. So here there's no lensing yet. What we need to do is see how the distortion tensor applies to Qij. Okay. So there could be some antisymmetric or symmetric contributions to the distortion tensor and how it affects this. The antisymmetric one is going to be only a rotation, and we don't care for that. We care about the shear, about how changes this. So we are going to consider only the symmetric distortions. And we can think of a transformation matrix that is going to apply multiplying Qij. So we have, first of all, the identity. If there's no lensing potential, the shape is unperturbed, plus the distortion tensor. And let me define now the distortion tensor as minus kappa. Oh, wait. I think, oh no, it's okay. Sorry. So yeah, this is minus kappa minus gamma 1, minus gamma 2, minus gamma 2, and minus kappa plus gamma 1. We're here basically by doing the comparison between this and this, the convergence that we defined before for the CMB lensing applies to the size of the object. It applies only to Q because it's the trace element. And the gamma components, which is the shear, applies to the ellipticity of the galaxy. That is one of the things that we are going to be interested. So basically what we need to do is apply this transformation to the definition of the flux and Qij, and basically it enters through the dependence of the angle of the source, the original angle, the perturbar angle, and the one with the diffracted angle and the contributions at higher order, in such a way that after accounting for this transformation matrix, so Qij observed, we have that it's 1 over the flux. The integral, and here we care for the unperturbed angle, is just a change of variable to do the to compare this with what we have directly. So this is going to be the Jacobian between the observed and okay, L. So this is the Jacobian changing from the unperturbed angle to the we can remove the indices, I think. From the unperturbed angle to the observed angle, the one that has been already deflected. And then we have here the the true intensity at the unperturbed angle, which is basically the same as the, I erased it already, but the same that the observed is the observed angle, as we saw before, and then just the change of variables for these two. So we have A minus 1 theta s evaluated for the I direction, and A minus 1 theta s evaluated for the J direction. And the flux alone is the same, but only with the effect of the Jacobian. So it's delta square ds, the Jacobian, and the true observed. So basically, if we compute the Jacobian, we see how the flux changes. So this is, at the end of the day, the Jacobian, we can get it out, and it's some magnification times the true flux, which is 1 minus kappa squared, gamma 1 squared, minus gamma 2 squared. So we have seen the first effect that the lensing will have in a point source, in a galaxy, and is that it gets magnified. But the way this gets magnified is not due to the fact that the actual photons get more energy or like there's more flux, because since what lensing does is only changing the path of the light, what we have through this magnification, which is coming just from the Jacobian, is basically a change of the size of the galaxy. Lensing keeps the surface brightness the same because it maintains the intensity. So if we see more flux, this means that the actual source, we observe it larger or smaller than what it is. Okay? So then the other effect that we have is that if we apply this, the Jacobian and this transformation here to linear order, we have that Q is the true one times 1 plus 2 times the convergence plus 2 the original ellipticity times the shear for 1 and the original ellipticity for the second component times gamma 2. The observed epsilon 1 is 1 minus 2 the true epsilon 1 times gamma 1 plus the second epsilon true times gamma 2, all multiplied by epsilon true plus 2 gamma 1. And for epsilon 2, we have this same factor here, but here is multiplied by epsilon true 2 instead of 1, plus 2 gamma 2. So at the end of the day, if we measure how Q, epsilon 1, and epsilon 2 are distributed on the sky in a statistical way, since once we start adding many, many galaxies, the true components are going to cancel here all the time, we can infer kappa, gamma 1, and gamma 2, with the only difference that since kappa affects to the size and Q true doesn't go away, it's harder to obtain. So at the end of the day, you want to obtain especially gamma 1 and gamma 2 that come from the averaging of all the ellipticities. So basically what you have is you look to a patch of the sky, measure the shape of all those galaxies, average over all of them. Since the distortion metrics here, so gamma 1, gamma 2, and kappa, are going to be coherent for all those galaxies in the same patch, because all of them are exposed to the same lensing potential, you expect to all of them have the same, while the intrinsic ones are averaged out, and then you have, okay, I have the shear in this patch of the sky, I have the shear in this patch of the sky, so on and so forth, and you can compute statistics and power spectrum and so on and so forth with those shear. And that's basically when we can get from the description of how this affects to a single galaxy, the statistics on the galaxy with lensing and the information about cosmology. Okay. All right. So now assume that we have already done those averages over the patches, and we have a map of the shear as function of position on the sky. But remember that the shear goes as the distortion tensor, which is the second derivative of the lensing potential. That depends on the gravitational potential. So as with all the quantities that we have studied so far, since the lensing potential is equal to 0, and we can predict the lensing potential as function of a direction on the sky, what we do is compute the variance and the power spectrum. Now here we have something that is different from anything that we've seen before so far, because we want to compute the power spectrum of the shear that is a matrix, right? We have this component here, here. So in this case, we want to use something that we can treat easier than a matrix. If we can avoid working with tensor, is much easier. And at the same time, this specific shear is defined, putting specifically the center at 0, and the values for gamma 1 and gamma 2 and kappa change if we make rotations for a given quantity. It's like the Navier-Stokes parameters for polarization. If we make a rotation, those values are going to change. So what we want to do in order to avoid that is to express the distortion tensor in terms of E modes and B modes. Okay. Also, since we are working in the flat sky limit because weak lensing affects to very small scales, we are working, as we did before for the CMB, in terms of the two-dimensional Fourier space, and the distortion tensor with like a minus here is going to be just Li, Lj over lensing potential. Okay, and we are going to decompose this in a V mode and an E mode, which in the case of the CMB, of the weak lensing, we can deal with it as with the light polarization. So this is a pseudoscalar quantity, and basically gets the curl type components with respect to the deflection angle, and this is a scalar quantity and gets the divergence type contributions from the deflection angle. However, remember that the deflection angle is already a gradient, and the curl of a pure gradient quantity is 0. So we know that from weak lensing at the linear order, as we are using all the time, B has to be 0. And this actually is used as a consistency test for systematic sin-over maps. Like if we try to compute the B-mode correlations for a shear map and it's not 0, we have some systematic sin-over data that we need to care for. And on the case of the E-mode, basically we get E of L as the gradient, the second derivative of the distortion tensor minus the trace, which at the end of the day is equal to 1/2 L squared of the lensing potential, which, as we saw before, I removed it. For the CMB lensing, this is the convergence as function of L. So from measuring the shear and getting the E mode of the shear, at the end of the day, we get something that is equal to the convergence. And what we can do is directly take the power spectrum of this convergence map, but project it to the CMB. Sorry, to the galaxy distribution. Okay. So we can work in a very similar way that we did for the lensing reconstruction of the lensing potential from the CMB, but there are a couple of differences. If you remember, for the lensing potential, we had some integral from 0 to the large scattering surface of some quantities and the gravitational potential. However, here we have many galaxies along the line of sight, and we want to see how this affects. So first of all, the first changes is that we have undetermined number of samples and distributed with some Resi distribution, which we can directly write as dn over dk. This is the number density of galaxies as function of distance to us. Now, we also don't know exactly which is the distance for each of the galaxies for us because we work with photometric surveys. And this basically introduces photometric redshift uncertainties. So if we express, as we did before, the convergence as function of the matter distribution, our power spectrum in the end looks like something like this. Kappa, kappa. Where basically what we are doing is transforming what we can predict very well, which is the matter power spectrum as function of Fourier mode in 3D quantities. We do the two-dimensional projection, and these are two kernels that account for the line of sight integral for the lensing potential and also our distribution of galaxies. So if we have now that the lensing potential in our case, for this case, is the generalization of that equation, but for the time that we have many values for the distance to the source, this is equal to 2 times. Now we have from 0 to infinite the integral. Here we have the factors for the tension, we have the gravitational potential, and for that last factor that depends on the distance to the source, we need to account for our uncertainty to do that. So we need to account for each specific distance here, all the potential sources that we have that contribute to this lensing potential. So here we need to integrate over distance, over the galaxy distribution, and times that factor that we had there. So in that way, we describe and plug this dependence on the gravitational potential with all this dependence on the distance into these kernels for the effects of the lensing from the matter power spectrum after doing the Poisson equation and so on. And what we get is, as it was the case for the CMB lensing power spectrum, that our lensing or convergence power spectrum, depending on the large scale structure through the matter power spectrum, weighted by some line of sight integral of the lensing potential, that in this case, it depends on the distribution of our sources. So here there are a couple of things that are going to be important for tomorrow. Since we are in distances that are much closer to us, the scales involved, or the scales that you can probe for the with the galaxy weak lensing involved much smaller scales of the power spectrum in the 3D distances, and therefore here basically we are including all the time the non-linearities in the matter clustering of the power spectrum. And that may seem like inconsistent with the treatment that we did, that keeping the lensing and the deflection angle always at the linear order. But it's actually not, because the effects that we have in the deflection angle through lensing are much, much smaller than the non-linearities from clustering. So we can keep everything at linear order for the lensing, but for the matter clustering, we need to include the non-linearities in the matter power spectrum. That could have been also the case for the weak lensing of the CMB, but the impact is smaller because here we are pushing to much smaller scales. And one of the main sources of uncertainty is that even if this is the matter power spectrum and there's no effects from bias and so on, if you go and push to very small scales, you have the effects of baryons that push away and was your clustering. Imagine, for example, that if you go to galactic scales, you can have an AGN that pushes the baryonic gas and also affects a bit through the gravitational pull the clustering of dark matter. So all that astrophysical effects affect the nonlinear power spectrum at very small scales and need to be very controlled in order to measure this matter power spectrum. And obviously the lensing power spectrum that depends on it. There is also an important effect here, and is that the lensing power spectrum depends both, and this was also the case for the CMB lensing, on the matter clustering and on the geometry of the lens system. And this is why the tension between the CMB prediction for the clustering and the galaxy weak lensing is always stated in terms of a variable that is S8, capital S8, which is basically the sigma 8 that we defined at the beginning of the class, times omega matter over 0.3 to the 1/2. And this is basically because from weak lensing constraints, if we plot the constraints that we get from weak lensing in sigma 8 and omega matter, we get some constraints that are like this kind of bananas. And actually, the quantity that they are most sensitive to is in this direction, which is exactly sigma 8. So the best constraint that we can get from weak lensing is in this parameter combination, and is basically due to the fact that sigma 8 controls the amplitude of the power spectrum, and omega mater controls all these co-moving distance factors, and therefore also changing the geometry of the lensing potential. Okay, so this is everything that I wanted to discuss today. Just to mention a couple of things. One of the other main systematics that I didn't mention, but I think that Sarah is going to discuss it this afternoon a bit, is the intrinsic alignment, and it's basically the fact that maybe there are some correlations in the actual intrinsic ellipticities of the galaxies. This is due to the tidal fields, which is the anisotropic pull of the gravitational potential, and affects actually the shapes of the galaxies, and is correlated at larger scales. And also the fact that we can also do something similar to the CMB lensing tomography that we discussed before, but with the galaxy weak lensing. Since here it depends on delta, on the overdensities in matter through here, we can cross-correlate galaxy weak lensing with galaxy clustering. And that's the kind of analysis of 3 times 2 that surveys like DES and KITS have done in order to improve the constraints from weak lensing. But there are people that are starting to add also CMB lensing to that, and even like I think like thermal Sunay Seldovich and all these kind of things, because since all of these quantities are depending on the distribution of matter on the large scale structure, you can basically throw all of that, because everything is going to be spatially correlated. And this is a way to improve individual constraints, because the sources of noise are different, the bias is different, you get some sample variance cancellation due to that, and especially to control some of the systematics that you may have, because different maps will have different systematics, and it's going to be very unlikely that those are correlated between them. Okay, so this is basically the description that I wanted to do for galaxy and CMB weak lensing. These are the two main measurements of the large scale structure that is in tension or participate in the tension with the CMB. And even though there are other, there's like measurements of the Lyman alpha force and so on that we'll discuss very briefly tomorrow to see what can be probed with everything in the matter power spectrum. But tomorrow the class is going to be a bit more chill. It's going to be mostly discussion, going through what the model will need in order to solve either the clustering tension that we discussed today or the Hubble constant tension that we discussed earlier during the week. Perfect. Thank you very much.